Neutron stars, some of the densest objects in the universe, are explored in this study using the linear relativistic mean field (RMF) theory, with a focus on phi and sigma asterisk operator meson interactions. The presence of hyperons and delta resonances significantly impacts the structure and evolution of these celestial bodies. Hyperons soften the equation of state, reducing the maximum mass of neutron stars, known as the hyperon puzzle. To address this, the authors employ the sigma cut scheme, enhancing repulsive interactions between baryons and ensuring the stiffness of the equation of state. The role of delta resonances, less explored due to uncertain coupling parameters with nucleons, is also examined. These resonances further soften the equation of state, creating a delta puzzle. By introducing the sigma cut scheme and adjusting the coupling parameter x sigma increment between delta resonances and nucleons, the authors study the impact of these interactions on neutron star properties. The research examines the effects of phi and sigma asterisk operator meson interactions on particle number distributions, equations of state, mass-radius relations, and tidal deformabilities of neutron stars. The inclusion of strange mesons sigma asterisk operator and phi in the RMF theory provides a more comprehensive understanding of the interactions between hyperons and nucleons, offering an alternative approach to overcome the softening of the equation of state. The findings suggest that strange mesons appear at around 3 ρ 0 and reduce the critical density of baryons in the high-density region. As the coupling parameter x sigma increment increases, delta resonances suppress hyperons, shifting the critical density towards lower values. The early appearance of delta resonances may play a crucial role in the stability of neutron stars. The paper highlights the impact of delta resonances on the equation of state, which is predominantly softened in the low-density region. Tidal deformabilities are calculated and compared with astronomical observations, such as GW170817, revealing that the inclusion of delta resonances decreases the radius of neutron stars. This work contributes to ongoing research on neutron star physics, shedding light on strong interactions within dense nuclear matter and the complex interplay between various degrees of freedom in neutron star interiors. The study of neutron star matter incorporating hyperons, increment resonance, and strange mesons is conducted using the IUFSU model. Table I presents the properties and fundamental constants for baryons other than nucleons, including strangeness mass, third component of isospin, charge, total angular momentum, and parity for various hyperons and increment baryons. The IUFSU model's theoretical framework includes the baryon octet, 2 leptons, and increment resonances, with strong interactions between baryons mediated by isoscalar scalar mesons, isoscalar vector mesons, and isovector vector mesons, each with their respective masses and coupling constants. The Lagrangian density of hadronic matter, given by equation 1, incorporates self-interactions of isoscalar mesons necessary for an appropriate equation of state for symmetric nuclear matter. The relativistic mean field model is employed, where meson field operators are replaced by their expectation values using the mean field approximation. The IUFSU model's parameters are listed in Table 2. The Euler-Lagrange equation yields the equations of motion for baryons and mesons. The IUFSU model is used to investigate the effects of strange mesons and increment resonance containing hyperons, utilizing the sigma cut scheme. The study examines the properties of neutron star matter, including hyperons and increment resonance, and the density dependence of the symmetry energy. The IUFSU model's predictions for the equation of state and composition of neutron star matter are presented, highlighting the impact of strange mesons and increment resonance on the properties of dense hadronic matter. The research findings demonstrate the significance of incorporating hyperons and increment resonance in the study of neutron star matter, highlighting the importance of the IUFSU model in understanding the complex interactions within dense hadronic systems. In the realm of relativistic mean-field models for nuclear matter and compact stars, equations of state, EOS, play a pivotal role. These models aim to capture the intricate dynamics between nucleons, meson fields, and baryonic resonances in these high-density astrophysical objects. A systematic set of field equations has been outlined, governing meson hyperon and baryon couplings, which are crucial for interpreting behavior within these systems. The key to interpreting the behavior of compact stars lies in understanding the coefficient information related to the b/s tau contributions, as well as the constant lambda, which is essential for calculating the energy per baryon, EQU, with detailed specifics on the calculations needed. This includes assumptions about the scalar linear ratio, radius, and the three-body force term, which is not included in the presented paper. The study also examines the importance of the choice of coupler G lambda in calculating the additional Lagrange term, which is considered necessary for fitting experimental data. Two assumptions are made: the small variation in the model's significant contribution to the total energy and the requirement of a small Cour-S term. This approach is supported by previous studies that have shown that a small variation in the models can significantly affect the calculated energy per baryon. The paper further discusses the use of a four-order term in the Lagrange, which is considered necessary for explaining the observed behavior of compact stars. The requirement for a small Cour-S term is also discussed, as it is essential for fitting experimental data and providing a consistent description of nuclear matter at high densities. In addition, the paper highlights the importance of considering the variation in the model's contribution to the total energy, as this can significantly impact the calculated energy per baryon. The study also emphasizes the need for further research into the properties of compact stars, particularly in terms of their composition and structure. Overall, the paper provides a comprehensive overview of the role of equations of state in relativistic mean-field models, emphasizing the importance of accurate coefficient information, the choice of coupler G lambda, and the necessity of a small Cour-S term. The study underscores the need for continued research in this field to better understand the behavior of compact stars and improve our understanding of nuclear matter at high densities. The IUFSU model is employed to investigate the equation of state of neutron star matter, with model parameters listed in Table 2 and scalar meson-hyperon coupling constants presented in Table 3. The pressure expression is given by equation 11, and the Tolman-Oppenheimer-Volkoff equation, presented in equations 12 and 13, determines the mass-radius relation and other relevant neutron star quantities. Additionally, the tidal deformability of a neutron star is calculated using equation 14. To stiffen the EOs, the sigma cut scheme is introduced, which involves adding an additional sigma self-interaction term to the model, as shown in equation 15. The parameters alpha and beta are set to 4.822 times 10 caret 4 m_n caret 4 and 120, respectively, following ref. 33. The value of C sigma is adjusted to 0.15 to satisfy the constraint on the maximum mass. The effective mass of nucleons versus baryon density is plotted in Fig. 1, demonstrating the sigma cut scheme's impact on the IUFSU model. The results show that the scheme does not alter nuclear matter properties at saturation density but significantly suppresses the sigma meson field strength above saturation density. Fig. 2 illustrates the emergence of sigma asterisk operator and phi mesons at high baryon densities and the increase in the rho meson field strength in the high-density region. The sigma cut scheme's effect on the EOs is examined, revealing that it stiffens the EOs by quenching the decrease of the effective nucleon mass above saturation density. This result is crucial for understanding neutron star matter properties and the behavior of mesons at high densities. The findings contribute to ongoing research on the equation of state of neutron star matter and the role of mesons in determining its properties. In the context of relativistic mean-field (RMF) theory, the role of mesons in dense nuclear matter is explored, focusing on the effects of sigma asterisk operator and phi mesons on the equation of state, EOs, and particle population. The inclusion of these mesons significantly impacts the field strength, particularly for rho and strange mesons, as depicted in Fig. 2. This variation in meson strength may contribute to a stiffer EOS. In RMF theory, scalar mesons, sigma and sigma asterisk operator, provide attraction, while vector mesons, omega and phi, provide repulsion. The changes in meson strength due to the inclusion of sigma asterisk operator and phi may contribute to a stiffer EOS. Fig. 4 illustrates the relative population of particles as a function of baryon density for different values of x sigma increment 1.05, 1.1, 1.15, with and without considering strange mesons. When sigma asterisk operator and phi are taken into account, the critical densities of Xi0, Xi-, and increment plus shift towards lower density regions, while the critical densities of increment plus and increment 0 shift towards higher density regions. As x sigma increment increases, the critical densities of lambda 0, Xi0, and Xi- move towards higher density regions, while those of leptons move towards lower density regions. Notably, as x sigma asterisk operator delta increases, the increment plus resonance appears, and the overall critical density for the increment resonance decreases, pushing the appearance of hyperons to lower density regions. Table IV lists the threshold densities NCR for the increment resonance in dense nuclear matter for different values of XSD. The effect of the sigma cut scheme on particle population is examined in Fig. 5, which plots the population as the chemical potential mu decreases. The increment plus and increment plus populations increase as the charge neutralization progresses. Key findings include the significant impact of sigma asterisk operator and phi mesons on the EOS and particle population, the shift in critical densities for various particles as XSD increases, and the appearance of the increment plus resonance as XSD increases. These results provide valuable insights into the behavior of dense nuclear matter and the role of mesons in shaping the EOS. The introduction of delta resonances in neutron star matter significantly impacts the equation of state, particularly in terms of baryon population and overall EOS. Without the sigma cut scheme, delta resonances lead to an increased relative population of particles such as Xi and delta as neutralizers of positive charges, compared to leptons. This is evident in Figure 5, where the critical value of delta resonance shifts to lower density, while the critical density of hyperons moves towards the high density region as x sigma increment increases from 1.05 to 1.15. The relationship between delta resonance and strange mesons, sigma, phi, remains unchanged, regardless of x sigma increment variations. The pressure as a function of energy density is explored in Figure 6, with and without the inclusion of strange mesons. While strange mesons have a negligible effect in the low energy density region, they slightly stiffen the EOS in the high energy density region. As x omega increment increases, the EOS becomes softer in the energy density range from 300 MeV, FM³ to 600 MeV, FM³, but significantly stiffer for energy densities greater than 600 MeV, FM³. When the sigma cut scheme is applied, the EOS is significantly stiffened, as shown in Figure 7. This stiffening is attributed to the truncation of the sigma meson field strength, depicted in Figure 3. Interestingly, the inclusion of strange mesons in this case leads to a softer EOS, which could potentially constrain the radius of the neutron star, although the maximum mass does not exhibit significant changes. The introduction of delta resonances and the application of the sigma cut scheme have profound implications for the composition and properties of neutron star matter, influencing the relative population of particles and the overall equation of state. The mass-radius relationship for neutron stars is explored in the context of the IUFSU model, incorporating the increment resonance and strange mesons, sigma asterisk operator, phi. Figure 8 demonstrates the impact of varying coupling parameters x sigma increment on the maximum mass and radius of neutron stars. The introduction of the increment resonance reduces the maximum mass and radius, while increasing x sigma increment from 1.05 to 1.15 leads to a decrease in the maximum mass. However, implementing the sigma cut scheme with a stiffer equation of state, EOS, boosts the maximum mass beyond 2m circled dot operator, aligning with constraints from gravitational waves and nicer data for MSP J0740 plus 6620 and PSR J00300451. The tidal deformability of compact stars is examined in Figure 9, comparing the results to the constraints imposed by the GW 170817 event. The sigma cut scheme with a stiffer EOS yields larger values of lambda 1.4, exceeding the GW 170,817 constraint. In contrast, the softer EOS without the sigma cut scheme satisfies the GW 170,817 constraint, resulting in smaller radii. Including the increment resonance in the softer EOS maintains lambda 1.4 within the bounds of GW 170817. These findings underscore the necessity of considering the increment resonance in the softer EOS, given the strong constraint imposed by the observational tidal deformability of compact stars during the GW 170,817 event. The importance of the increment resonance and strange mesons in neutron star models is highlighted, particularly in relation to the mass-radius relationship and tidal deformability. The results emphasize the need for a softer EOS that includes the increment resonance to satisfy observational constraints from both gravitational waves and NICER data. Future gravitational wave events from binary neutron star mergers are expected to provide measurements of the neutron star's tidal deformability at 2.0 m circled dot operator, further refining our understanding of these phenomena. The study delves into the influence of strange mesons on neutron stars, with a particular emphasis on the sigma-cut scheme's role in enhancing these celestial bodies' maximum mass. By employing the sigma-cut scheme with a value of c sigma equals 0.15, the calculated maximum mass and radius of neutron stars closely align with constraints from NICER, MSPJ 0740 plus 6620. However, the tidal deformability surpasses the constraint from GW 170,817 for neutron stars exceeding 2 m circled dot operator. Future gravitational wave events from binary neutron star mergers may provide new constraints on tidal deformability. The research also explores the effect of X sigma increment on the delta resonance, noting that as X sigma increment increases from 1.05 to 1.15, the critical density of hyperons shifts towards the high-density region, while the critical density of the delta resonance moves towards the low-density region. This suggests that an early appearance of the delta resonance may contribute to the stability of neutron stars. Furthermore, with increasing X sigma increment, the equation of state softens in the low-density region, resulting in a significant reduction in the radius of neutron stars, although the maximum mass remains almost unchanged. The findings are supported by neutron stars, the densest objects in the universe, pose a significant challenge to understanding the equation of state, EOS, of dense matter, which determines their properties. The hyperon puzzle, a long-standing issue in astrophysics, arises when the appearance of hyperons in neutron stars leads to a softening of the EOS, resulting in stars with smaller radii and masses than observed. To address this discrepancy, researchers have explored various solutions, including the consideration of delta resonances. This study investigates the effects of delta isobars on neutron star properties using a relativistic mean-field model with a new parametrization for the delta isobars. The inclusion of delta isobars in the EOS significantly affects the maximum mass and radius of neutron stars, potentially resolving the hyperon puzzle. Furthermore, the presence of delta isobars impacts the stability of hybrid stars, composed of both hadronic and quark matter. The authors demonstrate that delta isobars lead to a sequential phase transition in hybrid stars, resulting in a more stable and stiffer EOS. The novel approach presented in this study highlights the crucial role of delta isobars in determining the properties of compact stars, providing a key to understanding the observed masses and radii of neutron stars. The results suggest that incorporating delta isobars into the EOS of neutron stars may provide a solution to the hyperon puzzle, offering new insights into the composition and behavior of these enigmatic celestial bodies. The research paper presents a comprehensive list of 17 distinct types of cyber attacks, categorized into 4 primary groups: network-based, software-based, hardware-based, and human-centric attacks. Network-based attacks include reconnaissance, exploitation, and denial-of-service attacks, which target vulnerabilities in network protocols and infrastructure. Software-based attacks involve exploiting vulnerabilities in software applications, such as buffer overflow and SQL injection attacks. Hardware-based attacks focus on compromising hardware components, including sidechannel and fault injection attacks. Human-centric attacks, including phishing and social engineering, exploit human psychology and behavior to gain unauthorized access to systems. The paper also discusses the concept of attack graphs, which represent the sequence of events and interactions between attackers and defenders. Attack graphs are used to model and analyze the progression of cyber attacks, enabling the identification of potential vulnerabilities and the development of effective countermeasures. The authors propose a novel approach to constructing attack graphs using a combination of graph theory and machine learning techniques. The methodology employed in the study involves a comprehensive review of existing literature on cyber attacks, as well as the analysis of real-world attack scenarios. The authors also conducted experiments using a custom-built testbed to validate their approach. The results show that the proposed method can effectively identify potential vulnerabilities and predict the likelihood of successful attacks. The paper highlights the importance of understanding the complexities of cyber attacks and the need for a comprehensive approach to cybersecurity. The authors argue that traditional security measures, such as firewalls and intrusion detection systems, are insufficient to prevent modern cyber attacks, and that a more proactive and adaptive approach is required. The study contributes to the development of a more comprehensive framework for cybersecurity, incorporating both technical and human-centric aspects.